All right, so let's see how we did here. So probably the easiest way about looking about this was using the inspection method. You can see that in experiments 1 and 2, the oxygen was held constant, whereas the nitrogen monoxide doubled. And if it wasn't apparent to you, you could have divided 5.64 divided by 1.41. You would have got the same 4x there, as if you would have kind of just rationalized your way through it. So what you have is a 2x change in concentration, but a 4x change in rate. So that's not a linear relationship. That is a exponential second order relationship. So you should have concluded that nitrogen monoxide was second order. In a similar fashion, you could have isolated reactions 2 and 3, seeing that nitrogen monoxide had been held constant there. The oxygen concentration had doubled, and the value had doubled here as well. Little trick with exponents there. Since you could notice that the second exponent was 1 larger than the first. If that's the case, just move this decimal place 1 point over. So, you're comparing 11.3 versus 5.6. And so you can see there that that's where it doubles. So a doubling of concentration yielded a doubling of rate. That's a linear relationship. This is a first order relationship. So the overall rate law would have been R is equal to the concentration of, K times the concentration of NO squared times the concentration of oxygen to the first. So the order of nitrogen monoxide was 2, order of oxygen was 1. Overall order, we add those together, it would have been 3. All right, any questions with that before we move on? Okay, so we're going to move on then into the next kind of method, the method of integration, the integrated rates. And where this is going to be more important and more useful for us is when it is considerably easier to track the concentration of a reactant compared to that of a product. Because what we're going to do is we're going to graph the concentration of the reactant against the amount of time that elapses. And we're going to end up with a graph that looks like this, with time on the horizontal axis and concentration here on the vertical. And what we will notice is that the relationship, what kind of graph we get, will help to dictate the order of the reaction itself. So while it is possible to monitor the different kinds of graphs exponentially. We could look at power series and those kinds of things to graph. What we'll find is that working with a linear plot is going to be the easiest, because in general, we all understand slope-intercept form. And slope-intercept form is very easy to work with. And so these integrated rate laws are no different. What we're looking for is linearity. And how we get to that linear graph is going to help to determine what the order of reactant is. So there are three different linear plots that we are going to be looking at. One corresponding to 0, one corresponding to first order, one corresponding to second order. In a zero order reaction, the rate of disappearance of the reactant is completely independent of how much concentration there is. That's the very definition we've been working with all along. And so if we look at it from that standpoint, the relationship that we get is that the rate of reaction is equal to the value of the rate constant, whatever that rate constant is. And so zero order plots, by their nature, are already linear. So if I'm looking at the concentration of A over time, what I'm going to find is that that rate of disappearance isn't going to change regardless of whether we're at the beginning of the reaction or at the end of the reaction. And so if I want to look at the concentration at any given point in time, so let's say I want to look at the concentration at that mark right there, all I have to know is what time are we at, where did we start, and what is the slope of this line. The slope of the line here is equal to the opposite of the rate constant. So if I want to know how much of reactant A is left after 250 seconds, all I need to know is the rate constant and how much we started with. And I can figure it out because it's a linear trend. So zero order is very easy to see because the plot itself is a linear one. Where this graphical method can get a little bit complicated is when we start looking at first order and second order. Because in first order and second order, their plots look very similar. If I'm looking at the plot of a first order reactant, what I'm going to see is some kind of curved path. And so if I look at it directly, there isn't a whole lot of information that I'm going to be able to get out of it just by looking at the concentration versus the time. But if I do the integration properly, and that integration that we're talking about here is natural log, if I convert this to a natural log plot, now I get that linear line that I saw in that zero order. I have to manipulate the concentration a little bit. but I get that linear value. And the slope of this line, just like the previous, is equal to negative k. So your book likes to put first order graphing in those kinds of terms where you've got that ratio inside of the natural log. I actually don't like that way because it takes us out of the slope intercept form. And like I said, we've all taken algebra 1, algebra 2. We understand slope intercept form of graphs. So I'm going to rewrite this bottom equation in slope intercept form. And it's going to be the natural log of the concentration of A at any given time t is equal to negative k times the time plus the natural log of A at time 0. So A at time 0, that's our initial concentration. And again, just like with the method of inspection, the method of initial rates, initial concentrations are what we're going to start with. It's the easiest thing for us to measure because we know how much we started with when we put the stuff together. So this becomes our way of doing things. And if it's first order, we get that nice, easy linear plot. The only thing that we have to worry about is if we are looking to use this graph to figure out the concentration, we have to understand that the graph isn't going to give us the concentration. The graph is going to give us the natural log of the concentration. If we want to get rid of that natural log, we've got to use that natural exponent. E to the natural log of A gives you concentration of A. So that's first order. With second order, again, the problem we run into is that if we graph just the concentration of A versus time, we're going to see the same curving that we saw with first order. And so just by looking at it, we're not going to be able to determine if it's first order or second order. The way that we're going to have to determine it is to do this integration, manipulation of the concentration to figure out which one gives us a linear plot. And the manipulation for second order is the reciprocal. 1 over the concentration of A will give us this linear plot. The difference, since we are looking at a reciprocal, over time it's going to increase rather than decrease. And so in this case, our slope, instead of being equal to negative k, it's equal to positive k. Because again, the slope here is positive instead of negative. Here we do have the correct representation in slope-intercept form. So again, this is y is equal to mx plus b. So To find the concentration at any given value, again, using the graph, I'm going to have to remember that that Y value is the reciprocal of the concentration, not the actual concentration itself. So again, the question that might be going through your head is, well, why would you do this? Why go through all of this torture of graphing it? Well, the reality is some chemical reactions are slower than others. So the one that we're doing today, we can measure it in a scale of minutes from start to end. And that lends itself very well to the method of initial rates because because it has a very definitive endpoint, we can measure, okay, it started here, it ended here, it took 2 minutes and 36 seconds. Let's change the next variable. Let's change the next variable. Let's change another variable. And we can do about several trials in a matter of a couple of hours. But some reactions are a good bit slower. Some don't lend themselves to a very quick reaction's over. And so we end up using other kinds of methodologies to do it. So the lab that you're doing on Tuesday, you're going to be looking at a purple dye, and it is going to be gradually losing its color over the period of 20 minutes. And at the end of the 20 minutes, it's still not going to have completely lost its color. But using instrumentation, using a spectrophotometer, we can gauge how purple the solution is at various points along the way. And we can graph at various points along the way to monitor, okay, what's going on with that dye? How quickly is it disappearing? This is where this method becomes useful. And so this method is going to be at the heart of what we do on Tuesday for that kinetics of dye lab, for that first formal lab. And so here are some actual descriptions, actual pictures of some of these reactions going on. So here's the first order decomposition of ozone into oxygen and oxygen atoms. And here are some other graphical representations. Here is on the left, you have a first order reaction. So we can see the natural log plot being very linear here. Here we have a second order reaction on the right, showing a linear plot as we monitor the concentration of nitrogen dioxide. Let's do an example problem together here, though. Now, for this example problem, we're going to need a little bit more resource than what we have currently. So I'm going to... So what we're going to need for this is Excel. And so I've got a copy of Excel open here. We're just going to need to input the data from the table in. And so what we will do, and this is very similar to what you would need to do to solve a problem like this is you're going to make 3 graphs. You're going to need to make a zero order graph, a first order graph, and a second order graph. Now, right now, all we have are the data for zero order. We only have the concentration and the time. What we have to do is we have to add those other 2 columns and then tell Excel to calculate them for us. So equals ln for natural log and then repeat for everything else equals 1 over the concentration and repeat for everything else. So now I have all of the data that I need. Now it's just a matter of graphing. Insert scatter plot. And then quickest way to do it, one of the nice things about Excel, they have these quick layouts for you. Since we're looking at linear trends, this one right here with the FX in it, layout number 9, automatically assumes a linear trend, calculates the equation of the line and the R squared for you. And so I think we can pretty clearly see from this one that this is not a linear trend. So zero order is kind of out of the question here. If I control click and drag, I can highlight these 2 columns, do the same thing, insert scatter plot. And then with my quick layouts, layout number 9. This is showing a perfectly linear plot. So chances are pretty good that it is first order. For the sake of completion, we'll go ahead and make the second order plot here as well. Scatter plot, layout number 9. And not surprisingly, you can see this one's very curved. R squared is actually worse. So just as a refresher, remember R squared is the measure of the linearity of our scatter plot, our trend line. The closer it is to 1.00, the more linear it is. The R squared of 1 indicates a perfect line. All the data points fit on the line of best fit. So going back to the question here, test the validity of the assumption that the decomposition is first order. Yeah, we've done that. That was the scatter plot that we made. Determine the value of the rate constant. Well, remember, rate constant for a first order plot is equal to the opposite of the slope. So if I go back here, the slope was negative 0.0069. That would be what I would record Now, as far as units are concerned, since it is first order, remember first order, we're taking molar per second and dividing it by molar in the first degree. So we would need to record this value as either reciprocal seconds, 1 over s, or seconds to the -1 power to give this the proper unit. Now, another question that you might have is, well, what do I do about significant figures? It seems like most of these values have at least 3. This only has 2. How do I fix that? And the way to go about that is you can tell Excel how to treat the numbers and get your values up that way. So here under chart options, I believe. Yeah, format trend line label. You can go to label options and you can set it as a number and carry it out to however many decimal places are necessary to give you your sig figs. Or you can switch it to scientific. To get you the same way. Now, if you're doing this in Google Sheets, it's a little bit harder to toggle that, but it is doable. We can talk about it in lab. But I just want to point that out there because we should always be mindful of significant digits, especially when we've taken such great pains to monitor concentration precisely. It's usually kind of a shame to do all that work to maintain a certain number of digits in our measurements to then round all of them off later on. All right, any questions with this example? So if you are given a data table that looks like this, that is what you'll have to do with it. So if you're just given a concentration versus time kind of thing, know that that's integration, that you're gonna have to do the graphing. If you're given one of those big long tables with all the rows and columns, that's your method of initial rates there. All right, the last thing that we want to talk about here today, or actually 2 concepts. One of them is the concept of a half-life. Now, you might remember we talked a little bit about half-lives at the very end of Chem 105. The idea that radioactive decays have half-lives. Now, the part that we didn't bring in at the time, because we didn't have the context for it, is that those radioactive decays are first order decays. They obey first order kinetics, which is why they have a very set half-life that does not change regardless of their concentration. In general broad terms, half-life describes the amount of time it takes for half of a reacting species to react. And depending upon what kind of reactant we're dealing with, the half-life of its shelf life varies. Now, for first order reactants, we can see that the half-life of those reactants has nothing to do with their concentration initially. In fact, this 0.693 number, that is actually the natural log of 2. Now for the others, for zero order and for second order, we can see that the initial concentration does play a role. And depending upon which one it is, it either has a positive effect, makes the half-life longer, the bigger it is, or in the case of second order, makes the half-life shorter the bigger it is, because we know that second order reactants react much faster. Now, one important thing about half-lives that is pertinent and relevant to us, these equations that were given come from a direct manipulation of the integrated rate law. So if you are caught in a position where you can't find the equation and you need to calculate a half-life, we'll use zero order as an example here. The zero order rate law looks like this. Now, if we're at the half-life, whoops, wrong number. If we're at the half-life, that concentration at that given time is just half of the concentration initially. So if I substitute that in, subtracting each side by the initial concentration, I would get negative AO over 2 is equal to negative K T 1/2. And dividing each side by negative K, I would get initial concentration over 2K is equal to T 1/2. You can use that logic for any of these. Substitute AO over 2 for AT, manipulate the slope-intercept form accordingly, and you'll get natural log of 2 over K for first order. 1 over K times the concentration for second order. So if you're ever stuck in that bind, you don't have the equation sheet right in front of you, or the equation sheet you're looking at doesn't have this on there, understand you can derive it. And it's not hard to derive because all you're doing is making one small substitution. You're basically taking whatever that initial concentration is and cutting it in half. So if you actually have the values, it's even easier to do. My initial concentration is 1 molar, half-life would be 0.5. So I stick it in, 0.5 is equal to negative KT plus 1. If I know what K is, I can figure out the rest. It becomes a matter of algebra. All right, let's look at this sample exercise. The decomposition of dinitrogen pentoxide to dinitrogen tetroxide and oxygen is first order. Suppose that K is equal to 6.93 times 10 to the negative third reciprocal seconds with an initial concentration of 0.375 molar. What is the concentration after 95 minutes? Or, excuse me, what's the concentration after 3 minutes? Well, to do this kind of calculation, we have to understand, first of all, we have a discrepancy in our times. K is given to us in a seconds value. T is given to us in a minutes value. So we're going to have to do that conversion. 60 seconds in every minute means that we are talking about 180 seconds here. So we got to get that one out of the way first. Since it is first order, natural log of N2O5 at a given moment is equal to negative K 0.00693 reciprocal seconds multiplied by time, 180 seconds, plus the natural log of the initial concentration, 0.375 molar. Since all of these here on the right-hand side of the equation are numerical, I can add them together. My reciprocal seconds and seconds cancel. When I add everything together, it's going to be in molar units. So negative 0.00693 times 180 plus the natural log of 0.375 is going to give us a value here of negative 2.23 molar. To get rid of the natural log, we have to use the natural exponent, E. E to the natural log of N2O5 is equal to E to the negative 2.23. So after we do that, we get a concentration of N2O5. That is equal to three significant figures, 0.108 molar. All right, question we always want to ask ourselves after doing a calculation like this is, does this make sense? And really the only context that we have is the value that we end with smaller than the one that we started with? And the answer here is yeah, it is. How long will it take in minutes for 95% of the initial concentration to decompose? All right, so this time around, we can do this a number of different ways. Since we're given percentages, we're not given actual values, we really can set up this any way that we want, so long as our measurement at time is 5% of the initial. So for me, the easiest way to do that is to use those numbers exactly. Natural log of 5 is equal to negative 0.00693 reciprocal seconds times time plus the natural log of 100. Sorry? Because we're looking for when does 95% decompose, decay. So that means that 95% of it reacted, only 5% of it is left. So the natural log of 100 is 4.61. Natural log of 5 is 1.61. So doing some algebraic moving around, subtract each side by 4.61. I get negative 3.00 is equal to negative k times t, which is going to give me a t value. So divide by negative 0.00693 of 433 seconds. Which if I divide that by 60 seconds per minute would be 7.22 minutes. All right, question with this one? All right, so the last piece that I just want to mention involves a technique that, again, we will use this technique in Tuesday's lab. Involves, well, what if I have what if I have a reaction that has multiple reactants? And I need to use integrated rates to do it. How do I know that the reaction that I am seeing is a result of the nitrogen monoxide and not the ozone? Well, what we can do is we can create pseudo-order kinetics if we flood the reaction vessel with so much of one of the reactants that even when the reaction is over, the concentration of that reactant barely changes. So let's just say, for example, and we'll use simple terms here. Let's say that we have 1 unit of nitrogen monoxide and 100 units of ozone. After we're done monitoring the reaction, we have half of a unit of nitrogen monoxide left, and because of the stoichiometry, we have a 99.5 units of ozone. This is what we mean by the concentration practically did not change. Relative to each other, if I'm monitoring the concentration of nitrogen monoxide, I'm going to see that the concentration does vary considerably. It's lost half of its value. the ozone's lost 0.5% of its value. It's practically gone unchanged. And in that circumstance, since it hasn't changed, we can effectively consider that concentration of ozone to be a constant. And so what we do is in our graph, we graph using only the concentration of the nitrogen monoxide to figure out what the order of nitrogen monoxide is. And from there, we go, okay, we monitored it. It looks like it's first order. And we can say that it's first order because we've basically negated the effect of ozone. Now, we're not done there, unfortunately. We'll have to eventually go back and look at the effect of ozone as well, but we can do that in a number of ways. Looking at how the integrated graph changes. Let's say that instead of 100 units of ozone, we start with 200 units of ozone. Well, now this value of K prime, the graph, that can now change because the constant inside of it has changed. And so we can monitor the change in the constant to figure out how ozone played a role in it as well. And I've said this a couple of times, this is exactly what we're going to be doing in Tuesday's lab. There are two reacting species in that violet lab. There's the dye itself, and there's the hydroxide ion that decolorizes it. So what our job is going to be is we're going to amp up the concentration of the hydroxide very, very, very considerably and monitor what happens to the dye. And then once we figure out what the dye is, then we'll change the concentration of the hydroxide and see if that has any difference on the value of the slope of that graph that we made for the dye. And then we can kind of work it backwards. So that's kind of looking ahead a little bit, but that is where we're going to stop for today. Go ahead and just give a quick little bit of feedback here before we close out.